This is the most sleep-deprived bug I've ever made. Minus, plus. So the problem we're looking at today is not a usable problem, and it's on the coding website of Luogu, which everything on there is in Mandarin, and I don't trust Google Translate, so here's my summarization of the problem statement. Quite straightforward. You have n items, 5e4, which means n log n probably. The ith one has the size of ci. You can split them into several continuous groups, that is like substrings, continuous ones, and a group from j to I is the size of j to I is basically the distance between j and I and the sum of all the size of the individual items in j to I. And notice how it's not the number of items between j and I, it's the difference between j and I. So that's like the number of items minus 1. The cost of a group with size x is not just x, but it's x minus L squared, where L is a given constant. Now you want to compute the minimum cost to split the n items. So you can pause the video and think about it yourself. I think my sleep-deprived little bug here might have already reminded you of something if you have learned this trick before. Okay, I don't expect you to be able to do this if you have not learned this classic trick called convex hull optimization. But this is, however, the template problem for this trick. So first of all, this is obviously a DP problem. It gives off such a strong DP vibe, I believe probably a lot of people will be able to sense it. However, the classic way of doing DP, where you just transition from a previous J, will cost you an n squared time complexity. And the usual way of optimizing with a DP like this is like monotonic Q, obviously, and it would not work here because we have the squared. Monotonic Q does not work when we have the squared. So we have to use another type of optimization that kind of works like the monotone Q, but is even better, and that's the convex hull trick. Okay, so first of all, let's make this equation simpler. Rather than x minus L squared and x is defined as this, let's keep track of a prefix sum s, so then we can compute the sum of all c from j to I more easily. And then we can just rewrite the equation into, if we group the last items j to I, then obviously we have the cost to group items, the first j minus one of them, and then we have I minus j plus this thing obviously squared. And then we do all that stuff. But notice that if we transition like this, every time we'll at most be able to transition a substring of length 2 and nothing less. Because, well, if we want to use a data structure optimization like monotone Q or convex hull, as I'll be explaining here today, we can only insert the j minus 2 when we were processing the j minus 1, and the only thing, the closest to I that will be in the data structure will be j minus 2, which gives a length of 2 instead of 1. So that poses a problem. I don't know if you understood what I'm saying here, but okay, you'll see. So this is what I do instead. So we have fj plus I minus j minus 1, and then si minus sj, and not sj minus 1 this time. Notice how we added the minus 1 here and deleted the minus 1 from over here, because this time we're actually doing what if we group from j plus 1 to I. So that's why we have the cost of grouping first j, because the jth one is not in the last group anymore. And then we have the cost of grouping j plus 1 to I. So that is the cost, obviously. And then we start expanding this equation. So convex hull is one of those tricks where they just work, but you know why they work, but you just don't know why someone will possibly do that. So you don't know they work until they work. So you basically start expanding the equation. If you don't know this trick, you will not know what I'm doing at all, but you just keep expanding it, keep expanding it until you get a form kind of like this, which at first glance you think there's nothing special with it, but then you realize that, look, this whole term only has to do with j. This whole term only has to do with I, and obviously the constant. And this term only has to do with j, and this term only has to do with our answer that we're looking for, and I. So what does that do? Well, once again, you still can't really know what it does until you know what it does, because convex hull is one of those tricks. But notice how it's kind of like in the form of an equation for a line. So this is the y coordinate, and we have the slope, we have the x coordinate, and we have the y-intercept. Does it kind of look like that? So we have basically y equals this thing, that's this part. We have k, which is the slope, equals this part. we have the x value, this, and we have the y-intercept down here. So what can we do with this now? Well, notice that since answer is in the y-intercept and is what we're trying to minimize here, we are basically trying to find a point J where our current slope will go through and result in the minimum y-intercept. So what does that mean? Basically, we have all the y values computed out just using the J. So each J can basically mean a point on the coordinate grid. And each I can mean a slope of a line because the slope is solely determined by the I. So if I pull up a drawing here, you'll understand better. See, convex hull trick, it does not make sense until you do a few problems and it just start making sense for no reasons at all. Just like my second problem ever using this trick, and it's also barely making sense for me too. But here we have a coordinate plane. Nice, and this is the origin. And say we have a point right here. See, that is a valid J that we can use. And we know that for each J, we can find a point on the coordinate grid with it because the x and y value are all only according to J. And we know that for each I, we can find a slope without knowing what the J is. So then we just have, so say we just have a line here, right, of this slope, right? And then the y-intercept is just going to be, like for this one, if we go through this J, it's going to be right here. And say we have a different J, then the y-intercept, say we have a different J right here, and say we have a different J right here, and another one. And then we move around our line once again. Okay, this is not working. Anyways, you can basically see what I'm doing, right? You move around the line and you lay on one of those points. And it still doesn't quite make sense to you, but notice how the slope of this line is only determined by I, the points are only determined by J, the y-intercept is what changes along with the answer, so we're trying to minimize the y-intercept. We can kind of do a little something here that lets us find the optimal J very quickly, and that is called maintaining a convex hull. So I'm going to use a different color here. So say first, let me just add a few more points. So we have all those points. Notice how when we're trying to find the minimum value, only these J's actually matter. They are the only ones who can possibly result in the minimum y-intercept. Because for any line that goes through this point, it's like that, no matter what it is, this one, or this one, or this one of these three can always result in a lower y-intercept. And same for this one. This point, or this point can always result in lower y-intercept. And why is that? Well, because we are only keeping the points on this so-called lower convex hull because, okay, so first let me clear the definition for this lower convex hull. The definition is the slope of every two adjacent point on this hull is always increasing. And that's a definition for a lower convex hull. And the slope for an upper convex hull is always decreasing monotonically. So with this definition of the convex hull, we can once again look at why this point will never result in the lowest y-intercept no matter what the slope of this I is. Well, because think about it. Let me try drawing a line again. It's going to be painful. Have another line like this. Okay, now I can move it around. Because think about it. The slope of this line to right here. Okay, actually this is not a good point because it's right on top of this. Let's just take a look at this one. The slope of this point to right here would be higher than the slope from here to here, right? And that's why we discarded this point, because let's say this point is a little bit more to the left. I'm not going to erase it because then I can't move around this line anymore. Let's say this point is a little bit more to the left. So at first it was part of the convex hull, but then we add another one down here. And notice how the slope between those two are less than the slope between this. That means whatever line, if we put it right here, is going to be better now than if we put it here. Because, well, the slope of this one is lower, and that is going to result in a lower y-intercept. You can take a moment to process that, and I know I did not explain it very well. but you can kind of visualize it, can't you? The slope between the two adjacent points on the hole and the y-intercept. Okay, now that we know why the convex hull is always the optimal, there's still the biggest question here. How do we determine which point on this hole is going to be the optimal? Because even though we already got rid of a few options, there's still a bunch left, and we still don't know which one is going to be optimal, and we can't go through all of them. Well, the answer is the one that this line, the slope for which the slope of this line fits right between the left and right. So for this case, it'll be this one because the slope of this line is slightly more than the blue line, and the slope of this line is slightly less than the blue line. And why does this work? Well, think about this. Since we're trying to find the lowest y-intercept, say we move it just a little bit up here, notice how since the slope of this line is even lower than the slope of this line, the amount we lower the y-intercept by through lowering the line on the y-coordinate wise is going to be take greater effect than the increase in y-intercept because we moved it to the right. Actually, no, bad example. For this case, both of them will be causing a decrease in y-intercept. But say, let me just tilt the line for a little bit. Yep, okay, that's better. No, wrong way. This way. Okay, so say we're right here, right? So notice how shifting it to the right will cost a lower in the y-intercept, but shifting up will cost a rise in the y-intercept. And if and only if the slope of this line is less than the slope of our blue line right here, do we move it to the right, because then we know the amount the y-intercept decreased by through us moving it is going to be, it's going to take a greater effect on the position of the y-intercept than the amount we moved it up by. Right? Think about it, because the slope is less. Right? Visualize it. Okay, and that obviously applies for here too, except the slope is much less, which is why both the y and x movement contribute to a lowering in the y-intercept. And same thing for over here, except I did not draw this very well. One of them should have a greater slope than the other, because obviously the slope should be monotonically increasing. But you get the idea. So that is the basic idea of convex hull optimization. It still doesn't even make much sense to me. So you're fine if you still don't understand it. You understand it after a few problems, which I have a few good ones. You can solve this one, obviously. It's a really, really classic one. It's just a template, and the problem statement is right here. And you can submit it on a link that I will be including in the comments below. And then we start, after we deprive the equations, well, what do? Now notice since the slope of the line is solely determined by I, okay, I can't find the thing. The slope of the line is solely determined by I, specifically Si plus I minus L minus 1. Notice how the slope is always monotonically increasing. Like, it never falls down. So for later i's, the slope is always greater, which means since every time we're finding the first spot at which the slope is less than the slope of our blue line, so basically like going until we find the first spot where the slope is less than our blue line, which in this case will be right here, right? But say the blue line has a slope of very small, okay, like this, right? Then this spot would not work. We have to go to this spot, and that will be the first spot with the slope greater than the blue line. Sorry, my bad. Greater. The first spot with the slope greater than the blue line. So say if our slope is like this, then it'll be this spot, right? And notice since the slope are always monotonically increasing, I'm talking about the blue line slope will always monotonically increase as I increase. The point that we tangent, yeah, it's kind of like a tangent. The point that we tangent this hole on is always going to move right. So basically, we can delete this point once we find out that this blue line doesn't even fit for this point. We just like delete it, and then we go to the next one. And if it still doesn't fit, we delete it, because we know that it doesn't fit this one. It's not going to fit the later one either, because the slope of the later one will only be bigger monotonically. So that is the first notice. And second notice is that since the x-coordinate is solely determined by the j, and look how the x-coordinate is also monotonically increasing, we can just add the points to the end of the hole, which makes it a lot easier to maintain than the dynamic hole, which you will be experiencing few videos if I decide to do a video on dynamical. That's quite complicated because in that case you have to add points in the middle of the convex hull, which will be weird. So in this case, you're lucky and it's monotonically increasing, and you just have to add at the end, and that is much easier to maintain the monotonicity of the slope of the lines. And then you have the code. It's actually really simple. Calc is the answer. After we find the optimal j, we have to calculate the answer, right? Find is finding the optimal j, where we basically just pop every single line if the slope is even less than our current slope, and because we know that all the later slopes are going to be even bigger. And then we calculate the slope, obviously, y over x, and then the y and x coordinate are all given solely determined by j. And then the slope of the current line is determined by I, like this. And this is where our bug come in. That's what I did. And you can guess how long it took me. 2 hours. 2 hours. I went through the entire process, and this is why I kind of understand convex hull now. Because when I was trying to debug it, I went back through the entire process, understood everything, and I graphed it out literally and did all that thing just to find that I turned a plus sign into a minus sign. And immediately after I fixed it, like the whole thing's done. And there wasn't a single bug. And there isn't a single bug before. There wasn't a single bug after I fixed this one. So this is like the only bug in the entire code. And this is a pretty complicated problem. So I got lucky, not making any other bug. And the only one I make happens to be a plus sign written as a minus sign. Okay, well, I fixed it. 2 hours, but I fixed it. Anyways, this is the convex hull trick in how you optimize DP, where you can't optimize. So DP is obviously you can optimize using monotonic Q if you can, but some DP you have multiplication which you can't optimize with monotonic Q, and then you have to use the convex hull trick, which hopefully after this video you have a brief understanding of it, and with this very bad graph you kind of understand why we had to get it to the first one with its slope bigger than it, right? And then if you turn the whole thing around, you have an upper convex hull, which is when you try to find the largest y-intercept, right? I bet these moving lines in the hole is going to be in your nightmares. Well, anyways, hopefully after this video, you'll understand how to solve not the musical problem. This problem. I will be posting the link in the comments below, and if you want, you can use Google Translate, but you don't even need to read any of the Mandarin on this website, because you can just use a submission and submit a program and see if it's correct. Or you can use Google Translate. But anyways, thank you for watching, and I will see you tomorrow.